Hello students, subscribers, viewers, future engineers. Here is Algebra 2, Part 2. So let's continue with the discussion on formulas, principles, and sample problems part on Pascal's triangle, the expansion of the binomial in the form quantity x plus y raised to n. Then we have the binomial expansion and the theorems involved. Then briefly on set theory. And we'll have the first example, and in part 3 we will complete the problems to be presented to all topics under Algebra 2. So we have Pascal's triangle, and this is the expansion so that you can expand binomials of the form quantity x plus y to the n. So again, this is only for quantity x plus y raised to n. For binomials with different terms, we can still use this, but the formulas involved should be refined and changed or modified so that this Pascal's triangle can also be applied to those cases. So it begins with 1, and this one here means this is quantity x plus y raised to 0. So then we have 1, 1 for the binomial quantity x plus y raised to 1. Then because 1 plus 1 is 2, then this is 1 and 1. Always remember that the ends would be 1 and 1. Then 1 plus 2 is 3 here, 2 plus 1 is 3, and 1 and 1. And 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and 1, 1. And so on and so forth for that pattern. And we have here 1, then notice that the number for second term is n in general, because this is supposed to be quantity x plus y square. This is for quantity x plus y cube, and this is for quantity x plus y raised to 4. So notice that the second and the second to the last numbers are equal to n. So again, this one here is quantity x plus y raised to 0, because the value inside raised to 0 is 1. So for instance, 2 plus 3 quantity raised to 0 is 5 raised to 0. That's why it is 1. Then this is for quantity x plus y raised to 1. So that's why you have 1x plus 1y, the expansion. Then this is quantity x plus y square raised to 2. So notice that if n is 2, we expect n plus 1 terms. So 2 plus 1, 3 terms. So that is for 1x squared plus 2xy plus 1y squared. And notice also that the exponent of the first term x descends by 1 from n to 0, while the exponent of the second term y ascends by 1 from 0, so there's no y here, y to the 0, to n in general. So this is for quantity x plus y cubed. So we have 1x cubed, and take note of the properties. 1x cubed plus 3x squared y, so the exponent of the first descends by 1 and the exponent of the second ascends by 1 from 0 to n, for first term from n to 0. So that's why the next is 3x, then y squared, then plus 1 y cubed. So therefore, this is for quantity x plus y raised to 4, and it is equal to 1x cubed plus 4x 1x to the fourth rather, plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1 y to the fourth. So I'm not expanding it anymore, but because of the pattern above and the properties, you should be able to expand that. And this is for quantity x plus y raised to n. In general, it will be expanded here, and we will derive a formula for the R term based on our observations and the properties I mentioned there. So these are the observations. One, the numbers in the Pascal's triangle correspond to the respective coefficients of the terms in the binomial expansion. So these are the I highlighted or make the numbers bold faces, the coefficients. Second, the exponent of x descends by 1 from n to 0, while that of y ascends by 1 from 0 to n. There are n plus 1 terms in the expansion. So I already explained that the exponent of the first term x descends by 1 from n to 0. So if it says x plus y cubed, so it is 1x cubed first. Then in the next x square, then we have y to the 1. 1x cubed, y to the 0. Then 3x squared, y to the 1. Then 3x y squared, then plus 1 x to the 0 y cubed. Oh, that's the meaning of that. There are n plus 1 terms in the expansion. So if n is 3, for example, then expect 1, 2, 3, 4 terms. So 3 plus 1 terms. In general, if the degree is n, or we have x plus y raised to n, then we expect n plus 1 terms in the expansion. And notice that the degree of each term is equal to n. So for instance, we have x plus y cubed. This is the degree of this term is 3. The degree of this term is 3. X squared 2 plus 1. The degree of this term is also 3. 1 plus 2. The degree of this term is also 3. You have y cubed. So we now ready to expand quantity x plus y raised to n. Notice that the first term is always raised to n. So that's why if you have quantity x plus y cubed, the first term is 1, then x cubed. The last term is 1, y cubed. So we are sure that the first term is raised to n. X raised to n, then aside from that, we divide everything by 0 factorial, because the exponent of y, the second term, is 0 here, x to the n, y to the 0. So the idea is whatever is the exponent of the second term, we divide the whole term by, in factorial form, by the exponent of the second term, but in factorial form. But anyway, this 0 factorial is equal to 1. And if you want to prove it that it is 1, try to do this. N factorial is equal to n times n minus 1 factorial. So if n is 1, we have 1 factorial, because n factorial is n times n minus 1 factorial. So 1 factorial equals 1, n is 1, then we have 1 minus 1 factorial. So 1 factorial is 1 in the left, equals n 1, then 1 minus 1 factorial is 0 factorial. 1 divided by 1 is 0 factorial. So 0 factorial is 1. So that's the proof. You can also verify it in your calculator. So the next term, the technique is you have to differentiate just the first term. So this becomes nx to the n minus 1, because the second term, in the second term of the expansion, the second term of the binomial appears with degree 1. So we have n, again, the technique is, it's like differentiating the first term x. So it is nx to the n minus 1, and whatever is subtracted from the exponent of x, that's the exponent of the second term y, and the whole term is divided by the exponent of y factorial, just like here. So this is the second term. If you check it with this expansion, then we have n is 3, x to the 3 minus 1, so x squared, then y divided by 1 factorial, which is still 1, right? Then the next is, because the idea is it's like differentiating the first term, so we have n times n minus 1 times n times quantity n minus 1, then the exponent of x this time is n minus 2, because we subtract 2 from the exponent of x, then the exponent of y would now be 2, and the entire term divided by 2 factorial. So n minus 1, x to the n minus 2, y to the 2, or y squared, then whatever is the exponent of y, divide the entire term by 2 factorial. Let's check it with this term in the expansion. 3, then quantity 3 minus 1 is 2, so 3 times 2, 6, divided by 2 factorial, which is 2 times 1, so 6 divided by 2 times 1 is 3. That's why you have 3 there. Then x to the 3 minus 2 is just x, and y squared. So it checks, and so on and so forth. Then plus, because this is for further n, greater than 3, greater than 4, and this is for all, actually. So let's continue. Plus dot, dot, dot. We have the r term, for example, and we will focus to the derivation of this. Then plus dot, dot, dot. We know that the last term is also raised to n, so we have y to the n. So let's focus on the r term. And I hope that you know the pattern already, and I hope that you can expand binomials of this form even without that Pascal's triangle as guide. So let's concentrate on the r term, and to study r term we study this first. So this is supposed to be the third term. So the r term is equal to, we are sure that there is n minus 1, then n minus 2, supposedly, dot, dot, dot. Then what do you think is the coefficient of that term? What should be the expression here where it ends? So for example, if this is the third term, it ends at n minus 1. So if this is the r term, where should it end? So this n minus 1 in terms of its position, which is supposed to be the third term. So if we expect it is 3, it's not 3, it is n minus 1. And to express minus 1 in terms of its position, remember this is 3, so it should be n minus quantity 3 minus 2. So for the third term, the coefficient stops, the factor stops at n minus 1 in particular. But if it is the r term, it should end, so for this third term here, it is n minus, because it is third term, 3 minus 2, right? Because 3 minus 2 is 1. So therefore, for the r term, it should end at n minus quantity r minus 2. Because the third term, the coefficient ends at n minus third term minus 2, right? So n minus 1. So this should be n minus quantity r minus 2. So it should end that from this pattern. Then x raised to the exponent of x, the first term, is n minus 2. With respect to its position, it should be n minus quantity 3 minus 1. So that 3 minus 1 is 2. So that's n minus quantity 3 minus 1, right? So therefore, this one, x raised to n minus quantity r minus 1 also. Then whatever is subtracted to the exponent of x, like for instance here, x minus 2, that's also the power of the second term y. So y raised to r minus 1. Then the whole term divided by the exponent of y in factorial form. I hope that you understood the explanation based on this observation and pattern. So, simplifying further, we have n minus 1, n minus 2, dot. If we simplify this, this is n minus r plus 2, right? And because the pattern is we have product that is descending by 1, so the next factor supposedly here is n minus r plus 2 minus 1, which is n minus r plus 1. So denominator r1 minus 1 factorial. And I'll write that, but in factorial form. I introduce, because the next factor here is supposedly minus 1 of this, so n minus r plus 1, right? Then I just make it in factorial form. I should also divide by the same factorial form so that I'm not changing the original coefficient. So that is 1. Then x raised to n minus quantity r minus 1, then y raised to quantity r minus 1. So notice that this product n times n minus 1, n minus 2, dot, n minus r plus 2 times quantity n minus r plus 1 factorial. So it is like, if n is 10, for example, it is like 10 times 9 times 8 times 7 times 6. Let us say this is times 5, and this is 4 factorial. Then 4 factorial is actually 4 times 3 times 2 times 1. Therefore, the numerator is actually n minus 1, n minus 2, up to 1. Or in short, the numerator is simply n factorial. And we write this as n minus quantity r minus 1 factorial. So n factorial over, so x raised to n quantity r minus 1, y to the r minus 1 over r minus 1 factorial. And we write this as n minus quantity r minus 1 factorial. Now letting a new symbol m as r minus 1, then this becomes n factorial, x to the n minus n, y to the m, over m factorial, then n minus m factorial. We will also let x as the first term, and I symbolize it with f, the second term y as s, second term, so that the r term would be n factorial, x to first term raised to n minus m, second term raised to m, over m factorial times n minus m factorial. Notice that if m is r, are you familiar with the formula? N factorial over n minus r factorial times r factorial. This is actually combination of n things taken m at a time. So in other words, this is NCM. So that the r term formula reduces to NCM, first to the n minus m. So take note that NCM is n factorial over n minus m factorial, which is this. So the r term is now NCM, combination of n things taken m at a time, first term raised to n minus m times second term raised to m. And remember that m is r minus 1. So this is the formula for the r term, and m is r term minus 1, or r minus 1. So this is the more compact form for the R term, and I hope you can remember it. It's easy to remember. NCM, combination of n takes taken m at a time. Then first term, the power is the difference of these symbols n and n. Then what? Remember the principle that whatever is subtracted to the power of the first, that's the power of the second. So s raised to m. So that's it. Then let me continue. We have properties of the expanded binomials. One, the first and the last terms are raised to n. So notice that we have x to the n, x to the 3 here, and y to the 3. So these properties are for quantity x plus y raised to n, where the exponent of x is 1, exponent of y is 1. But for this case, I change it so that the first term is now f, second term is s. This is applicable to any terms of the binomial, even if the exponent is no longer 1. So any term, even if the other term is constant also, and vice versa. Then corresponding symmetrical terms have the same coefficients. So for instance, if I draw this axis of symmetry, so axis of symmetry, 3, 3, same coefficient, 1, 1, same coefficient. This axis of symmetry, 4, 4, and 1, 1. Then this axis of symmetry, n, n, then 1, 1, so on and so forth. So notice that observation. Then the third observation, the sum of the exponents or powers of each term is n. So that is, the degree of each term is n. I already mentioned this. The expansion has n plus 1 terms, already explained. The exponent of the first term of the binomial is descending by 1 from n to 0, while that of the second term is ascending by 1 from 0 to n. Already explained also, and take note of the observation. Because of these observations, we can derive and generalize sum of coefficients of the terms of the expanded binomial. I'll call that S sub c. So for the case 1, this is the general binomial, assuming the binomial has terms ax to the p, then the exponent of x is not necessarily 1, plus by to the q, quantity raised to n. So take note that in the expansion, x raised to something would be present. So since we are just going to derive sum of coefficients, the technique therefore is, because these variables, if we assign them as 1, this cannot affect the coefficients of the expansion, because 1 raised to any power y, if you assign y equals 1 raised to any power, it is still 1. Therefore, the technique therefore in deriving the sum of coefficients is we just replace the variables by 1. So this becomes a times 1, which is just a, b times 1, which is just b, because if we replace the variables by 1, 1 raised to any power is still 1. So the replacement of the variables by 1 cannot affect the coefficients. So it is simply quantity a plus b raised to n. So for instance, 1 plus x plus y, quantity cubed earlier. So the coefficients were 1, 3, 3, 1, if you can recall. So that would be 8. So 1 plus 1 raised to n raised to 3 is 2 raised to 3, which is 8. So it checks. It also checks for other cases, even if the exponent of x is different and the exponent of y is different also. For case 2, general binomial, we have ax to the p plus k to the quantity raised to n. So in this case here, k is a constant. So therefore, if you use the principle earlier stated, then k raised to n will be accounted as a coefficient, where in fact it's not a coefficient because it is a constant. It is a constant term, so without variable. Therefore, if we still stick to this formula here and principle, it is accounted as a coefficient. In order to neutralize the accounting of k to the n in the formula, because of this, we must subtract k to the n, quantity k to the n also, in order to neutralize its presence. So that's the remedy. So the formula, therefore, for the sum of coefficients for this case is we still replace x by 1, and because k is a constant, and definitely it involves k to the n, and it is accounted for as a coefficient in order to, which is supposedly not, in order to neutralize its presence by accounting it as a coefficient, we must subtract quantity k to the n also. So therefore, this is the formula, quantity a plus k raised to n, and we must subtract k to the n. And that represents the sum of the coefficients for this situation here where the other term is a constant. So next is sum of exponents of the terms of the expanded binomial, S sub e. So for the situation quantity x plus y raised to n, because of these observations, take note the sum of the exponents powers of each term is n. Each term has a degree of n, as mentioned. Remember. Then, there are n plus 1 terms in the expansion. Therefore, the sum of the exponents would be degree of any term times the number of terms. So it is n, the degree of each term, and since there are n plus 1 terms in the expansion, it is n times n plus 1. So that's the sum of the exponents. But that is for quantity x plus y raised to n. Now about for this general binomial here. So we modify that formula by multiplying the average of exponents. So this is now the formula, n times n plus 1, because of this observation, applicable only for quantity x plus y raised to n, where the exponent of x is 1 and the exponent of y is also 1. But how about for this situation here, where the first term is f is ax to the p plus by to the q. So for the first situation, let's show that this is the formula. This is the formula because the average of exponents for quantity x plus y raised to n is the exponent of x is 1. The exponent of y is also 1. So the average is 1 plus 1 divided by 2, which is still 1. So that's why the formula for the situation x plus y raised to n for the sum of exponents is just n times n plus 1. But for this general case, it will be completed and applicable for any cases by multiplying it by average of exponents. So that's the technique or idea. Then let's proceed to set theory. A set is a collection of objects called elements of a set. So, any set is a subset. This is the symbol for subset of itself. A set without an element is called a null set or an empty set, or delta, or this symbol here. And because any set is a subset of itself, even if it is an empty set, this empty set has also a subset. What is the subset of the empty set? The subset of the empty set is the empty set itself. So therefore, the total number of subsets will be defined here. It is equal to 2 to the n. So for instance, if a set has 3 elements, 1, 2, and 3, there are 3 members, that set has 2 to the 3 subsets. To call them, we have 1, 2, 3, all of them, the set itself. That's the first. So let us show that there are 8 subsets. Then set with only one element, 1. So that's second. Another set with element 2, that's third. A subset with element 3, that's the fourth so far. Then subset with element 1 and 2, so that's the fifth. Subset with elements 1 and 3, that's the sixth. Subset with elements 2 and 3, that's the seventh. And finally, the empty set. So that's the 8. So that verifies that the total number of subsets is defined by the formula 2 to the n. Remember, the number of combinations of n things taken 1 or 2 or 3 or all at a time, it was n 2 to the n minus 1. There is minus 1 because it is the sum of combinations of n things taken 1 or 2 or 3 or all at a time. There's no combination if you do not take elements. So in other words, combination of n things taken 0 at a time is not there. So that's why there is minus 1. So take note of the relationship between the total number of subsets and the total number of combinations of n things taken 1 or 2 or all at a time. So that's it. You relate them so that you can recall. Two sets are equal if they have the same elements. Of course, set 1, 2, 3 is the same as set 1, 2, 3, or even if you rumble the elements. The intersection, which is denoted by this symbol, inverted U, of two sets is the set of elements common to two sets. While the union is, this is the union symbol of two sets, is the set of all elements that are in both sets. Then, the complement, denoted by S prime of a set, consists of elements in the universal set not found in the given set. So for example, in this statement, in the School of Engineering and Architecture students, or in division rather, the complement of engineering students would be the architecture students, because architecture students belong to SEA division. So that's an example. So remember that this intersection and union can be used in the solution of inequalities, remember, okay? Then n sub s, the total number of subsets, as already mentioned, I give you an example there, is 2 to the n. If there are 3 elements, 2 to the 3, 8, and I already mentioned those 8 subsets. So total number of subsets. Then let's have these problems for solution. This is the first. For in Algebra 2 Part 3, I will present examples, problems for solutions in the whole many topics in Algebra 2. So this is the first one. Find the sixth term in the expansion of quantity 2x cubed plus 9y raised to 11. So it's no longer x plus y raised to n. It's the general form of binomial. So in this case, n is 11. And because we're looking for the sixth term, and remember m for the formula for the r term is n combination m. First term, in this case, the first term is 2x cubed raised to n minus m times second term raised to m. The second term is 9y. Take note, the r term is as simple as combination of n things taken m at a time. First term raised to n minus m, second term raised to m. It's easy to memorize that formula. So n is 11. M is r minus 1, so 6 minus 1, so it's 5. The first term is 2x cubed, the second term is 9y. Therefore, the sixth term is NCM, first term raised to n minus m, second term raised to m. Substitute in this formula, 11 combination 5, then quantity 2x cubed raised to 11 minus 5, then quantity 9y raised to 5. So evaluate with your calculator 11 combination 5, then do not stop there. You multiply that by 2 to the 6. 11 minus 5 is 6. So times 2 to the 6. That is part of the coefficient. Then times 9 to the 5. So the result is 1,745,960,832. Then this is x cubed quantity raised to 6. So that's x to the 18. And of course, y to the 5. So the sixth term is 1,745,960,832 x to the 18, y to the 5th. So that's it for this video because it's quite long.